All right, so here's theorem 14.1, properties of double integrals. You can see that all the properties that you would hope to exist do exist. So if I want a double integral of a constant times my function, I can pull that constant out. If I take the double integral of a sum or difference of functions, I can separate the double integral. The double integral is always positive if your function is positive, and if f of x is xy is bigger than or equal to g of xy, then their double integrals should be satisfy the same inequality. This last property is one that maybe you wouldn't have thought about. This one says that if I wanted to take the double integral of f over some region R, I can break R into two non-overlapping subregions, R1 and R2, and separate my double integral over those two regions. This is just like if you were taking the single integral from a to b and c was some point in that interval from a to b, you could break up your single integral as the integral from a to c plus the integral from c to b. I think I've got a picture here of two non-overlapping regions, R1 and R2, and we're going to do an example here in just a second. All right, so let's go back to the notes. I just want to do an example and then let you try another problem. Okay, so let's switch back to black. Here we go. I want to set up integrals. Oops. Yep. For both orders of integration. And then do the more convenient one. Okay, so I'm looking at the integral over R of y over x squared plus y squared dA, where R is the trapezoid bounded by y equals x, y equals 2x, x equals 1, and x equals 2. Okay, so let's sketch R. Actually, let's take this to the next page because I'm going to run out of space here. Copy. Okay. So first let's think about our region R. So say here's x equals 1 and x equals 2. So we're going to do 1. I'm going to go 1, 2, 3, 4 on the y-axis. Okay, so y equals x. I'm going to plot 1, 1 and 2, 2. And y equals 2x is going to be 1, 2, and 2, 4. And there's x equals 1 and x equals 2. So here's my region of integration. Okay, let's start by setting it up taking horizontal slices. Okay, so horizontally simple. So what is the issue here? Well, if I'm down here, if I take a horizontal slice, x is going to go from the line x equals 1 to the line x equals y. You agree? But as I move up here, once I pass this dotted line that I've sketched, Now all of a sudden x runs from the line x equals 1/2 y to the line x equals 2. Does everyone see that? So what that means is I'm going to have to break up my region into two regions, R1 and R2, where this bottom half, is going to be R1 and this top half is R2. And so let's think about this. So x and the bottom half, let's look again. If I take a horizontally simple region in the bottom half, it goes from x equals 1 to x equals y. And y goes from down here, y equals 1, up to y equals 2. In R2, x is going to, run from the line here to the line there. So x goes from x equals 1/2 y to x equals 2. And y starts at 2 and goes up to 4 here. Right? All right, so if I want to set up the integral, I'm going to have to write it as two integrals. The first one is going to go from x equals 1 to y of y over x squared plus y squared. This was bounds on x, so dx. And then y runs from 1 to 2 dy plus over R2, I'm going to have x runs from 1/2 y to 2 of y over x squared plus y squared dx. And then on the outer bounds, I've got 2 to 4 dy. Okay. Now, what if I decided to go vertically simple? So now I'm taking slices like this. Now notice as I move along, I'm always running, y goes from y equals x to y equals 2x. So my bounds here, so this was horizontally simple. And now we want to do vertically simple. And now my bounds on y are just from x to 2x, and my bounds on x are from, well, x goes from 1 to 2. All right, so now the double integral becomes the integral from x to 2x on the inside of y over x squared plus y squared dy, and then the outer bounds are 1 to 2 dx. All right, so here are my two setups. Which one do you think is going to be easier to evaluate? Well, if I look at this top one, I'm integrating this with respect to x, and I've got x squared plus y squared in the denominator. That's going to be kind of messy to try to integrate. I like this one better, right? Because if I see here, I've got x squared plus y squared in the denominator, and I've got the derivative of y squared here up top. So I can use a u substitution to evaluate that. All right, let's go ahead and do it together just to make sure we're all confident on our abilities. So when I integrate this second one, I'm looking inside, integrating with respect to y, and like I said, I want to do a u substitution. So I need the derivative of the denominator in here. That would be 2y, so I need a 2, and I'm going to put a 1/2 out front to compensate for that. And now this is a 1 over u du. Does everyone see that? here's my u, and here's du. Okay, so I have 1 over u du. That integrates as natural log. So I still have that 1/2, 1 to 2, and this is natural log of the absolute value of x squared plus y squared evaluated from y equals x to y equals 2x dx on the outside. I have a 1/2 integral from 1 to 2 of the natural log of x squared plus 2x quantity squared minus the natural log of x squared plus x squared dx. So let's clean this up a little bit. So this becomes the natural log of 5x squared, and I drop the absolute value because that's going to be positive, minus the natural log of 2x squared dx. Okay, how well do you remember your rules for logs? I can rewrite a difference of logs as the natural log of 5x squared over 2x squared dx. And why was that helpful? Well, the x squared's canceled, right? So this is just the integral of natural log of 5/2 dx. I no longer have an x variable, so this is real simple to integral. I just have integrate 1/2 natural log of 5/2 x evaluated from 1 to 2. So 1/2 natural log of 5/2 times 2 minus 1, or 1/2 natural log of 5/2. All right, I'm going to pause and let you try a problem in WebAssign, and then we'll do one more example together.